Hi there, and welcome to this lesson on Further Pure Mathematics 2. And in this lesson, we're on Chapter 7, 7.5, and how you use Taylor's series to find series solutions of differential equations. Now, in the last lesson, we met the Taylor series expansion of f of x at the point x equals a. You can write it like that, or by replacing x with x minus a, you can also write it like that, with the normal conditions for validity. And it's this second version which is useful if you have a differential equation of the form dy by dx is some function of x and y, or d2y by dx squared is a function of x and y, or some other differential equations where an exact solution cannot be found by any of the standard techniques that we've learned so far. A small warning. A variety of different notations are used in textbooks and exam papers for showing how to do these questions. So, for example, given y equals f of x, you may see any of the three things written down. You may see f dashed of 0, you may see y dashed of 0, or you may see dy by dx with a vertical line and a subscript of 0 written down. This last notation is used in the textbook for the course, if you've got it. You'll notice that I tend to use these first two. Now, all three things mean exactly the same thing. They all mean the value of dy by dx, the first differential, when x is equal to 0. Okay, let's have a look at an example. Given d2y by dx squared plus y plus cos y is equal to 0, use Taylor series to find a series solution of the differential equation in ascending powers of x up to and including the term in x cubed. Given the initial conditions, when x is 0, y is 0, and dy by dx is equal to a half. Well, the Taylor series expansion of f of x about the point x equals a is that. It's the second version, and that's the version that we always use for this type of question. We're considering the expansion about the point x equals 0. That's because that's the value of x we were given in the initial conditions. We were told when x equals 0, y is 0, and dy by dx is a half. The most significant thing about that is that that gives us the value of a. So if we're considering the expansion about the point x is 0, then a is equal to 0 in this question. We're told this in the question: when x is 0, y is 0, and dy by dx equals a half. Writing that in function language means the same thing. When x is 0, f of 0 is 0, and f dashed of 0 is a half. We tend to use function language when we actually write down Taylor's series. So Taylor series is that at the point x equals 0. Now, there are four things that we need to know. We need to know what f of 0 is, f dashed of 0, f double dashed of 0, and f triple dashed of 0. Two of these things were told in the question. So we're told in the question when x is 0, f of 0 equals 0, and f dashed of 0 equals a half. That gives us both of these values. So in this question, we actually only need to work out two values: the second differential at 0 and the third differential at 0. Now, I'll let you have a go at working out how you do that. You do that using the differential equation itself. I'll see if you can make sense of it. So have a go yourself, pause the video, and then come back to me when you're ready. Okay, let's have a look at this. So that is the equation that we were given in the question. Writing d2y by dx squared as f double dashed of x in function language, but leaving those actually as they were. And then what we want to know is what the second differential is when x equals 0. Well, we just substitute that in with the value of y that we were given in the question. And the value of y when x is 0, that's f of 0. So y here when x is 0 means the same thing as that. So when x is 0, f double dashed of 0 plus 0 plus the cosine of 0 will equal 0. That simplifies to that, which gives us the second differential at x equals 0 is minus 1, which is the value we're going to have to write here. Now, to find the third differential, we just differentiate this equation. So differentiating this equation gives us f triple dashed of x, differentiating y gives us dy by dx. And using the chain rule to differentiate cos y, we get minus sine y dy by dx is equal to 0. Again, substituting in the conditions at the point we're considering, which is when x equals 0. So dy by dx, we were told in the question, that's equal to a half when x equals 0. And y is equal to 0 when x equals 0. So we just substitute those in there. That gives us the third differential at 0 is equal to minus a half. Now we can just substitute all four values into Taylor's series. So f of 0 is 0, we were given that in the question. F dash of 0 is a half, we were given that. F double dash of 0 is equal to minus 1, we worked that one out. And f triple dash of 0 is equal to minus a half, we worked that one out as well. And tidying that up, and changing f of x back to y, just because that's the form that they used in the question. They didn't use function language, they used a Cartesian language. So the answer would be y equals a half x minus a half x squared minus 1/12 x cubed. Okay, example 2. Given that d2y by dx squared is equal to this expression, first of all, differentiate that to show that the third differential, d3y by dx cubed, is equal to this. Has this form, you have to find the value of k. And then once you've done that, you're given the initial conditions, given that when x equals 0, y equals 1, and dy by dx equals 2. Use Taylor's series to find a series solution in ascending powers of x up to and including the term in x cubed. Okay, it's quite similar to the last question. I'll let you have a go at this yourself first. So have a go, pause the video, and come back to me when you're ready. Okay, let's have a look. So we were given in the question this, and that's what we need to differentiate. So differentiating the left-hand side just gives us d3y by dx cubed. And then we differentiate this using a mixture of the product rule and the chain rule. I won't go through all the detail, but I've written down e to the x and then differentiated what's in the brackets. That gives us this. And then I've written down what's in the brackets and differentiated e to the x to get e to the x, which gives us that. Factorizing, taking e to the x outside, and dy by dx is just the same thing as dy by dx squared. And joining these two y dy by dx's together gives us that. And that's in the form we were asked to find, where k here is equal to 4. So that's part 1 done. Part 2 says, given when x is 0, y equals 1, and dy by dx equals 2, use Taylor's series to find a series solution up to and including the term in x cubed. Well, the Taylor series expansion of f of x about the point x equals a is that we're considering the expansion about the point x equals 0. The significance of that is if we're considering about the point x equals 0, that means a equals 0. When x equals 0, y equals 1, and dy by dx equals 2. Writing that in function language, when x is 0, f of 0 equals 1, and f dashed of 0 is equal to 2. So rewriting Taylor's series, and we can now substitute a equals 0 in there. And we know f of 0, they told us that in the question, is 1. We know f dashed of 0, they've told us that in the question, it's 2. But like in the first example, it's the second differential and the third differential that we're going to have to work out. So to work out the second differential, we're using this equation here because it's got the second differential in it. d2y by dx squared is just f double dashed of x. So when x equals 0, this term here becomes f double dashed of 0. And then this term here, we're told that x equals 0, and when x is 0, y is equal to 1, and dy by dx is equal to 2. So we've just substituted all of that into there. And that allows us, well, simplifies to that, and then allows us to work out that the second differential at 0 is equal to 6. Now we need to do the same thing again for the third differential using this equation that we worked out in part 1. So when x is equal to 0, d3y by dx cubed is the same thing as f triple dashed of 0 when x equals 0. And we've substituted into here everything that we've either been told in the question or know. So x is 0, d2y by dx squared, we just worked out, that's 6. dy by dx, we were told in the question, is equal to 2. And y, we were told, is in the question, is equal to 1 when x is 0. So substituting all those values into there and tidying it up gives us that, which simplifies to the third differential at x equals 0 is equal to 30. Well, those are the two things that we need to substitute in here and here, which gives us f of x is equal to that. We can simplify these fractions, and just to go back to the language they use in the question, change f of x back to y, and that gives us the answer, y equals 1 plus 2x plus 3x squared plus 5x cubed. Those would be the terms up to x cubed. Okay, the last example. Given that x dy by dx equals 3x plus y squared, first of all, differentiate that to show this statement here, then differentiate it again to show this statement here. Given that when x equals 1, y equals 1, find a series solution for y in ascending powers of x minus 1 up to and including the term in x minus 1 cubed. Now, it's very similar to the previous two examples, except for two things. In the previous examples, we were considering around the point x equals 0. In this question, it's around x equals 1. So that'll mean that a is equal to 1. And the other thing, in the previous questions, we were told the value of dy by dx in the initial conditions. This time we're not. So there's three things we need to do in this question. We'll have to use this first question to work out dy by dx when x equals 1. This one to work out d2y by dx squared when x is 1. And then this one to work out d3y by dx cubed when x equals 1. Okay, that's the general idea. I'll let you have a go at doing the whole question yourself. So pause the video, have a go, and then come back to me when you're ready. Okay, let's have a look at this. So part 1, that's what we've been asked to show. Well, to show that, we just need to differentiate the question or the equation that we were given in the question. So differentiating the left-hand side using the product rule would give us that. If you differentiate 3x, we'll get 3. Differentiate y squared, we will get that using the chain rule. Tidying that up will give us that. And that's the form, oh, not quite, we just need to factorize these two terms here. And if we factorize those, then we have got exactly the form that they asked us to get in the question. So that's part 1 done. Part 2 asks us to show this, which means we need to differentiate our answer from part 1. So if we differentiate this, it's all quite long, there's a lot of differentiation going on here. Write down the x and differentiate the d2y by dx squared gives us that. Write down the d2y by dx squared and differentiate the x gives us that using the product rule. And then differentiating this using a mixture of the product rule and the chain rule will hopefully give you that. And differentiating the 3 just gives you 0. Tidying that up, the dy by dx times by the dy by dx is dy by dx squared. That's really the only thing I think that's been done there. But that is what they wanted us to find. Sorry, just going back to where we were. They asked us to write it in that form in the question, and we have done there. Okay, and then part 3 is asking us to use all of those things to find a series solution for y in ascending powers of x minus 1 up to and including the term in x minus 1 cubed. And you'll notice that in the previous examples, we just had x and x squared and x cubed. That was because x was equal to 0 in the initial conditions in the first two questions. It's because x equals 1 here that a equals 1, and we get x minus 1 and x minus 1 squared and x minus 1 cubed. That comes from this initial condition. X dy by dx is equal to 3x plus y squared when x is equal to 1. So substituting in x equals 1 and y equals 1 into that allows us to work out dy by dx, and that gives us dy by dx is equal to 4 when x is 1. And then to get the second differential, we're using the second equation. And again, we're substituting in everything that we know. So we know that x is 1, y is 1, and dy by dx is equal to 4 when x is equal to 1. Substituting all of that into there gives us this, and that allows us to work out d2y by dx squared, which is 3 plus 4, which equals 7. And then finally, we need to do the same thing for d3y by dx cubed. And again, we're substituting in all the 4 things we know. We're doing it around x equals 1, and when x equals 1, y equals 1, dy by dx is 4, and d2y by dx squared is 7. We substitute all of those into there. And that gives us this. And then rearranging all of that and tidying it up gives us that. And finally, d3y by dx cubed is equal to 32 when x equals 1. Okay, that's what we've done so far. Now, in this question, I've left the whole business about Taylor series really till the very end of the question. So the Taylor series expansion of f of x about the point x equals a is that's just the formula. We're considering the expansion about the point x equals 1, and at x equals 1, a equals 1. So whatever value they give you for x in the initial conditions, that is the value you use for a. So substituting a into the standard formula for Taylor series, that gives us that. And that's where the x minus 1 and the x minus 1 squared and the x minus 1 cubed come from. All we need to do now is substitute in these values for f of 1, f dashed of 1, f double dashed of 1, and f triple dashed of 1. So we've got those here. Rewriting all of those in function language, so it's just rewriting this line, would give us that. And then substituting in those values into Taylor's series would give us that. Multiplying out the brackets, no, we don't multiply the brackets, but all we've done there is change f of x into y and simplified this fraction here. Very little has happened on that last line. And that is the answer, which gets us to the end of this lesson. And if you've got the textbook, then turn to page 143 and have a go at exercise 7E. Thank you very much for listening, and cheerio.